Force fields, they're real. They're awesome. They're not yellow, they don't glow, and they don't make Superman bounce off them, but they're still pretty neat. Let's check it out. Electric fields, action at a distance. Coulomb's law gives us lots of questions we can't answer. And if we go out into the universe, we'll find more still. First of all, philosophically speaking, how does electricity know that other electricity is there? Think about it. How do electric charges, or anything else for that matter, exert force on each other without touching? Every force we did in mechanics, you had to touch, you had to push or pull, but electric charges don't do that. What do they do? How does that force propagate through space? Specifically, how fast does it travel? If you have a negative charge and you put a positive charge down next to it, when does the negative charge know that the positive charge has suddenly appeared and attract? Now, if you want to say positive charges don't suddenly appear, yeah, equals mc squared. There's a negative charge somewhere else, but it's farther away, so Coulomb's law says we do the positive charge first. Yes, in particle physics, particles can simply appear out of a vacuum as long as you're operating on conservation of mass and conservation of matter. Okay, so think about it. When does the negative charge know that the positive charge has suddenly appeared? Instantly, you said, right? Well, nothing can travel faster than light. C, formerly known as the speed of light, is the relationship of how many meters there are in 1 second of time. By definition, 1 second of time is the amount of time it takes something without mass to travel 3.0 times 10 to the 8th meters. That is 30 million meters. Light has no mass, so it has been up till the 20th century our gold standard. Nothing can travel faster than light, not even news. It is a violation of the laws of physics for the negative charge to know that the positive charge is there instantaneously. So, how fast does the news travel, and why? If this is all too philosophical for you, here's a practical question. Is it safe to stick my fingers in it? For instance, this big patch of nothing right here. Can I stick my fingers in it? Will I be okay? Yeah? How about this one right here, this set of 3 little holes? Can I stick my fingers there? No? Coulomb's law says, why not? After all, one patch of nothing is the same as the other. K, Q1, Q2 over R squared. If Q2 is 0, nothing else matters. So, where would I look to find electrical activity? How strong is the electrical activity? And if I stick my fingers there, am I going to get shocked? That is to say, in a more general case, is the electrical activity strong enough to make sparks? Other good things to know ahead of time. The answer relies on the use of the word if. If I stuck my fingers over here, I'd be perfectly fine. If I stuck my fingers in an outlet, I would not be perfectly fine. The point is, don't stick your fingers there to find out. We need something that helps you tell that something is safe ahead of time. So we ask the question, what force would a positive charge feel if it were put there? Not your fingers, not the wires that we're holding, but something hypothetical. We're going to call it a test charge. We are going to send these hypothetical, these imaginary test charges out. And if the test charge would feel a force, then we'll say there's electrical activity there. We're going to call this electric field. Electric field is defined in force in newtons per charge in coulombs. You already know this is going to be a very, very big number because the coulomb is impractically big from the start. Your official formula for electric field, first, best, and most definitional, is E, note that vector sign, oh boy does it have a direction, equals F, that's where the vector sign comes from, the direction of the force, towards or away, up, down, left, right, attract, repel, you figure it out, over the strength of the charge. This is little q, also known as Q2. Again, this is little q, also known as Q2. Most of the time there's only one q, you don't have to worry about it. But if this is in a Coulomb's law problem, this q is the test charge, it's the second charge. Electric field shows the force that a positive test charge would feel if it moved to that location. The electric field answers all our questions. How does electricity know that other electricity is there? The electricity gets its news via the electric field. That's how it knows. How fast can the news travel? Electric field is a force field. It has no mass. Therefore, news can propagate across the galaxy at 3.0 times 10 to the 8th meters per second. C, formerly known as the speed of light. Of course, that's pretty darn fast, which is why it looks instantaneous to you. When the news reaches the other charge via the electric field, that charge feels attraction or repulsion. If the electric field is weak, the force is very small. If the electric field is strong, the force is very big, and you probably shouldn't stick your fingers there. Force fields are hypothetical forces. A real force only exists if someone or something goes and finds out. Let's take a look at force fields in technology, laser printers and Xerox machines. Inside your laser printer or your Xerox machine is, to summarize, a parallel plate capacitor. One sheet of negative charge, one sheet of positive charge. If you were a positive charge in here, which way would you move? You'd move this way, right? Now these charges are spread uniformly in this picture that I found. However, in the real machine, the charges are not spread uniformly. There's a strong group of charges here and a weak group of charges here and no charges here and then a few more sprinkled there. So the field lines aren't uniform. There's a very strong field here and much weaker fields here and none at all here and then a little more here. Into the laser printer is spritzed a set of highly charged particles. We call them toner. Toner is not a liquid like ink. It's a solid. They're tiny, tiny dust-sized black flecks, and they are very highly positively charged. So when you spritz toner here into this space, the positives are repelled by the positives. They're attracted to the negatives. They go up, 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 and they cling to the paper because of the force of attraction between the negative metal plate behind the paper and the positive toner. Then a heat lamp is turned on. It melts the toner in place. Wait a second for the toner to dry, and out comes the paper over the top. This is why the paper is always warm when you get it out of a laser printer or copy machine, and why if you just can't wait to get to class and you grab your paper out of the top, you'll smear the melted toner all over your fingers. It's not ink, and that's why you have a devil of a time washing it off. And yet, if you put down your water bottle or your mug of coffee on the paper after it's printed and it leaves a ring, the water or the coffee doesn't actually smudge the ink the way it would smudge the ink from an inkjet printer, because it's not ink, it's toner. The toner melted. If you let it dry, it's now a solid, and it's stuck there forever. You can reproduce photographs, fancy serifs on fonts, and the works with this technology because these charged particles, these solids, are not drops of ink that you're spraying onto a page. They are guided with virtually laser accuracy by the electric field. You go here, you go here, you go here, and you're building the image dust fleck by dust fleck. How do we know how much toner to put there? Well, more force means more particles, means more toner. So here's our formula for electric field. Take out your calculator, do a practice problem. Let's say the charge on one of those toner flecks is 10 nanocoulombs. Look, it's the size of a piece of dust. Work those metric conversions. Notice you can't use nanocoulombs in the formula. It's got to be full coulombs in base units. And the electric field inside your laser jet is, let's say, a very small 2,000 newtons per coulomb. Pause. Find the force on a charged particle. To check your force, find the acceleration. Remember, A equals F net, and let's say there's only one force right now. Let's say this is happening horizontally, over M. Give the mass of a charged particle as something incredibly small, 1 microgram. Work your problem, plus play to check your work. Check your algebra. If you've done your algebra correctly, multiplying Q to the other side to get the formula F equals QE, you should be getting a force of 2 times 10 to the negative 5th newtons, or 20 micronewtons. And this may seem like a pretty small force, but toner is a pretty small particle. If you find the acceleration with a mass of 1 microgram, divide that force by mass, and you're going to get an acceleration of 20 meters per second, more than twice the acceleration of gravity, going upward and sticking to the part of the page that has that particular electric field. And that's why we can make these sheets so quickly, not by like this, what an inkjet printer does, back and forth printing the ink, but electric field making a whole page at once, sticking the toner to it, melting it, and printing. The next question, obviously, is going to be how do we set up the electric field? We're not always going to get 2,000 newtons per coulombs in a box. How do we set up the charges so we get the exact number we want? Well, that's a lot more complicated. Let's start with the first big obvious example, the one we already have the tools to do. Let's say we've got two charges. They're unitary. They don't have any significant geometry. Let's say they're metal spheres, make it real easy, and they're placed d, a distance apart from center to center. In that case, we already have everything we need to know about the electric field. Check it out. Electric field is force per charge, and we know the force between these two charges. It's Coulomb's law. We've been working with it for days. So, again, pause. In your notes, substitute in Coulomb's law for F. K, big Q, little q, over the distance between them squared. Press play to check your work and check your algebra. Ready? One of the little q's cancels out. Keep your numerator together. The denominator of a numerator is a denominator. One of the little q's cancels out, and you have the formula for electric field strength. K, Q, that is the charge you're working on, over the distance between them squared as measured from center to center. Now, here's the important thing. What does electric field strength depend on? If you want a strong field, what does this formula say you have to do? Pause, write down everything you can see that you can change, press play to check your work. First of all, electric field strength depends on the strength of the charge. If you have a bigger charge, you'll have a stronger field. Second, it depends on the distance between them. If you want a stronger field, get closer to the charge. Electric field depends on proximity. Now, let's apply this to the question of whether or not you can stick your fingers there. How close do you have to get before sparks can fly? Here we go, here we go, here we go. We got two charges separating. Whoa! Electric fields are strongest closer to stronger charges. How strong? At an electric field of 3.0 times 10 to the 6 newtons per coulomb, air ionizes and becomes a conductor. Sparks are electrons jumping through the air, which they can only do if the air is ionized, as per your notes on conductors and insulators. Ionized air is a great conductor, and whenever the air ionizes, this molecule here, and this one here, and this one here, but not that one over there, not that one over there, this one, and this one, and not that one, you can see the electrons connecting the dots from molecule to molecule, from ion to ion through the air. That's why lightning bolts are so ziggy and zaggy, and that's why you see them branching out in multiple places. You're seeing electrons traveling through wherever there are enough ions in the air. And you can see that up close to these very, very highly charged thunderclouds, you get incredibly, incredibly strong electric fields with lots and lots of electrons traveling through all those thick cords of ions, those thick areas of ions traveling down to the ground. This is the missing link we're looking for. Sparks will fly when the electric field is 3 million newtons per coulomb. Electric fields can also take us somewhere we couldn't go before with Coulomb's law, and that's in the interior of your device, where you can't stick your fingers because it's full of metal or full of wood or full of plastic. Let's take a look at conductors and insulators. We'll start with the metal. Here, check it out. All these electrons are free. They are free to move through the electron sea or the electron gas or whatever you want to call it. They can go anywhere they want inside the metal. And where they want to go is far away from these negative charges as possible. Does this work with positive charges? Sure, they'd all rush toward the positive charges. How far away can they get? The answer is the bottom surface of the conductor. All of them went as far away as they could until they were all clustered together on the surface. Now, if you were a net negative charge inside this conductor, if you were negative and we put you like here, you wouldn't go where the other negatives are going because all this is so negative already. You'd be caught between the negatives up here and the negatives down there, and the end result is if you were a net negative charge here, you wouldn't move at all. The next negative won't have anywhere to go, with the result that The net charge in a conductor resides on the surface. Write that down and put a box around it. It's incredibly important. The net charge, the extra charge, resides on the surface, and that means the electric field inside a conductor is zero. That's a separate fact. Keep your language clear and write it down. The electric field inside a conductor is zero. With all the net charge on the surface, the charges in the interior are completely balanced. A new one wouldn't have anywhere to go, that wouldn't be getting it closer to something that it's repelling or further away from something that it's attracting. Now, this isn't true on an insulator. For an insulator, you'll see that the charges rearrange themselves. They rearrange into little dipoles. Each molecule becomes its own dipole with a positive end and a negative end. This is because the electrons in an insulator are not free to move. They can go anywhere they want within the confines of their own molecules. They can get as far away from this negative charge as possible, but that's not the far side of the solid, that's the far side of the molecule. Now, in the end, you can charge by induction on an insulator, no trouble at all. There's a big positive charge here and a big negative charge here. The difference is in the interior. In the electric field simulator you'll be working with in the next lesson, you'll set up these little positive test charges. You can see they're white, and you'll see where they go. This cylinder is filled with an insulator, and you can see there is an electric field inside. Those particles are moving. They're not moving as fast as any of the ones that are free to travel in the air, but yes, there is an electric field inside an insulator. So, if you're in danger of getting struck by lightning, where do you want to be? Watch the Richard Simmons video from Top Gear that is next in the sequence, where Richard Simmons tries to find the safest place to be during a lightning storm. Take notes on what he finds and especially what he says about the tires.